For recording purposes, this is qualitative analysis. And to make things interesting, well, you already storyline there. Dracula has kidnapped 8 people from your village, and your job is to try to pay the ransom because he's holding them for a ransom. And these are the people, and this is the amount of money for each person's ransom, right? So as we go along, you're gonna earn money, and if you get enough money, you can pay the ransom and save someone from the dungeons of Dracula, right? Yeah, it's back in the times. $50 was worth 20 back then. Somebody said, all right. So we have to make some assumptions today, right? We did so much work already. The assumptions is, I'm going to assume that everybody knows the part of the atom by now: protons, neutrons, and electrons. You know which one is positive, you know which one is negative, which one has no charge. We've been through that, we've been down that road already. And last term, we did a lot of work on this thing called oxidation and reduction. By the way, with the charges, right? The oxidation and reduction have to do with the charges. You know, some things are like have a charge of +2, or some things have a charge of -2. When oxidation occurs, the charge gets larger. Like you go from 2 plus to 3 plus. Let us give you an example. Like if you have something that's 1 positive, if it changes from 1 positive to, let me say, 2 positive, if the charge got larger, well, then it's what? Oxidation. And reduction is just the opposite. If the charge gets smaller, it's reduction. For example, if something had a charge of +2 and then it went down to 0, it got smaller. So, and remember, negative numbers are even smaller. The more negative something is, the smaller the value, right? So, I know I'm saying it back because there's a whole term passed, but I can't go back the whole thing, obviously. That'll be unfair to the rest of the class, right? So, just saying it back one more time. When the charge gets larger, it's oxidation. When the charge gets smaller, it's reduction. And the name for reduction actually makes sense. Reductions comes from the word reduce. So I have a quick question here. If I have something with a charge of 0, right? So it starts off with a charge of 0, and then the charge changed to -2. Is that oxidation or reduction? It starts off at 0, so it has no charge, it's neutral, and then it goes to 2 minus. Is that oxidation or reduction? Right? And the class is what? Mixed on it. Which one is larger? Isn't 0 larger than -2? And negative numbers are smaller than 0, right? So it went from larger to smaller. This is a reduction. The charge got smaller, right? So be careful with that. When the question involves a 0, a lot of people get it wrong. They forget negative is smaller than 0. Okay? All right. Picture number line. Let's go. So how do we identify hydrogen, right? How do we know that there is hydrogen in the room or in a test tube? Well, first of all, I'll give you all a chance to write down, right? But I want you all to, pay attention for the time being and answer any questions I have. And then you'll get a chance to do what? Take down the notes. First of all, hydrogen is diatomic, meaning that in a neutral state, it always exists as 2 atoms, H2. A lot of people don't know this. They know the first one, sorry. They know hydrogen is colorless. You can't actually see hydrogen with your eyes. And the thing about hydrogen, it has no smell. So how do you identify? Well, down here, we have an experiment. So we put 2 things in a test tube. We have a liquid and we put a substance in it, and it produces a gas. Well, the test for hydrogen is this. If you put a lighted flame, right? A burning splint, right? Meaning a flame, it will make a popping noise. Okay. Now I know a lot of people are going to ask me the question. So, you sure you're not mixing up the hydrogen test with the oxygen test? I'm real sure. This is the hydrogen test, the one where the flame produces a popping sound, and you have to. And in the exam, I want you to use this phrase: a loud, squeaky pop. Please use that phrase. You go in almost any textbook, and that's the phrase they have. Now, in the CXC exam, they not only ask you for a description of what you observe when there's hydrogen, but they like you to give what? A equation to explain it. You see the hydrogen, right? You see when you have a flame, right? Remember, the only reason this flame is burning is because there's oxygen present, right? And remember, you cannot start a fire without oxygen. So when the existing hydrogen, right, mixes with the oxygen, it forms water. But look at this, eh? You all notice the symbol there? Whenever you use H2O and it has G next to it, right? Right? Whenever it has G next to it, it's a gas. In other words, it's basically steam. Remember, gas water is what? Steam. And because steam is hot, it kind of expands now. Now, I don't know if you all know this, but hot things do what? Expand. And the steam that is formed expands, and it's the expansion that creates the squeaky pop. Okay? Right? So instead of calling it steam, some people call it vapor. All right? Right. But the examiner is not going to ask you, why does it make a squeaky pop? I just give you some extra information there. Because it's a gas and it kind of expands, the expansion causes the popping sound. Right? You think everyone understands this? You don't have to draw the diagram below. That was just for me to talk it through. Right? There isn't too much to understand here. It's just, like I said, to read and remember and memorize the balanced equation. I already balanced it for you guys. Take down everything. Let me know when you are finished, please. The next test is oxygen, the one people mix up with hydrogen. So once again, oxygen is colorless and it has no smell, just like hydrogen. So how do you tell the difference between oxygen and hydrogen? Well, here's what you do. You all ever like light a match and out a match, but even though you're out the match, doesn't it glow orange a little bit? I'm sure everyone has seen that in real life. I'm assuming that you all are old enough to light a stove, right? Now, if the match is glowing, that is obviously not the same thing as a burning match. A burning match and a match that just out and just has a slight tinge of orange is two completely different things. You call that a glowing splint. And if you have oxygen like coming out of a test tube, once again, it doesn't matter what ingredients or chemicals we have in the test tube. All we know is oxygen is being produced. What will happen? The glowing splint, once it's exposed to the oxygen, it will start back to burn. It will relight the match. So that's different. The hydrogen, you need a burning flame, and that produces a squeaky pop. The oxygen has nothing to do with a burning flame and nothing to do with a with a squeaky pop. It just relights a glowing splint. Right? So once again, you don't have to take down the diagram. You just need to take down the table and the name of the gas. And oxygen is also diatomic. Let me know when you guys are finished. Right. Easy so far, right, guys? It's just to remember. So let's do the next one. Carbon dioxide. It seems a lot of these gases are colorless and have no smell, right? So carbon dioxide is no exception. Okay? So the test. What you need to get for this, you need carbon dioxide, right? You're going to get something called lime water. It's very, very popular in the chemistry lab. Now, the common name for this liquid is lime water, but the chemical name for it is calcium hydroxide. So what usually happens, right? When you bubble the carbon dioxide, like you send carbon dioxide, or in other words, easier way, if you mix carbon dioxide with lime water, you get a white precipitate, right? And this here is the reaction. You have the carbon dioxide here. Look at here, we got a different color. You have the carbon dioxide here, and you mix it or bubble it through some calcium hydroxide. The AQ means it's a solution, right? That's the, we'll put it here in case you all didn't realize that that's the calcium hydroxide. And when you mix these two together, you get something called calcium carbonate. But it forms, notice the letter S, which means it forms a solid. That's the white precipitate. Calcium carbonate is a white solid. And then you get some water, right? But the white precipitate you are seeing is calcium carbonate. Now, most most teachers, right? Not sorry, some teachers, I shouldn't say most teachers, right? Some teachers will stop up to here. So how much of you all know about this one? Because usually this one is introduced early in like almost the first term of chemistry. This thing about carbon dioxide bubbling through lime water, and you get this white precipitate. Right? It's even in integrated science. So if you were doing integrated science in Form 2 and Form 3, it would have also been introduced. Now here's the thing, right? If you do the experiment for too long, like when you now start to bubble the carbon dioxide through the lime water, you will see the white precipitate, the calcium carbonate solid. But if you do the experiment for too long, the white precipitate disappears. And sometimes in the exam, they just ask you to explain why. Why does the white precipitate disappear if you do the experiment for too long? And I have the answer here. You see, when the calcium carbonate forms, right? This same calcium carbonate that we just got, I'm putting it over here now. When the calcium carbonate mixes with more carbon dioxide and it have water, remember, the calcium hydroxide solution will have water in it. So after the calcium carbonate forms and it is white, and it continues to mix with the excess carbon dioxide and the water, it forms what? Calcium hydrogen carbonate. Now, here's the thing. Calcium carbonate is insoluble. So that is why it forms a solid. It cannot be dissolved. But then, when the calcium hydrogen carbonate forms, you notice it have an AQ. So that means calcium hydrogen is soluble. So because it dissolves, you are unable to see it, right? So it's very important that you don't do the experiment for too long, because in the first half of the experiment, you form something that's insoluble. That's a solid. And then when you continue the experiment, the solid thing that you just made bonds with the extra carbon dioxide and excess water to form something soluble. All right, and the examiner would ask you to write the equations, both equations, right? So take down everything on the screen, please. And you see how I put in the words insoluble and soluble? Take it down just like that as well, please. All right, so it's time to earn some money. So let me show you how to earn the money, guys. What we do, we go to the graveyard behind Dracula's castle, and we have to dig up 3 graves of celebrities. Choose any 3 celebrities, and let's see how much money you get. All right, so that's how we play the game. Choose any 3 celebrities of your choice, and good luck. Right? It's 3, you got to choose 3. All right, count up how much money you got. Like if you chose Bill Gates, Elon Musk, and Taylor Swift, it's 2 plus 7 plus 8. Also, if your grave has a skeleton hand, you get an extra $5. Each skeleton hand is worth an additional $5. So let me know how much money you got. Keep track of it. And then we're going to go to the dungeon and pay some ransoms. Okay? Now, you don't have to pay a ransom. You can save up your money. But if you decide to rescue someone, let me know who you rescue. Now, if you rescue someone, now if you rescue Bobby, and Bobby is $26, obviously you're minus $26, right? Because you're paying. So if you decide to rescue anyone, let me know who you rescue. And of course, if you didn't, let me know also. Somebody rescued Thunder, right? Somebody saying you're rescuing nobody. Somebody rescued Sasha, somebody rescued Bonnie, somebody rescued Rick, right? So update your money, update your money. All right, let's go. Let's do some more boring qualitative analysis. So the next gas that we have to know about is ammonia. Right now, ammonia is NH3. I'm hoping everyone knew that by now, right? So unlike all the other gases we did, carbon dioxide, oxygen, and hydrogen, ammonia is, well, it has a pungent odor. Yes, it is burn your nose. When you try it, when you smell it, it is literally burn your nose. But unfortunately, it's also what? Colorless. Okay. Now, if you read at the bottom of the screen here, right? I don't know if you all know this, right? Red litmus paper turns blue to indicate an alkaline compound, right? Because the red litmus paper is sensitive to OH ions. When we did acid and bases last term, I told you all basic and alkaline compounds usually have an OH in them, a hydroxide in them. And red litmus paper turns blue when it comes in contact with anything alkaline, right? Now, see if you can answer the question here. Something is missing in the yellow space here. Blue litmus paper is used to what? To detect acidic compounds. So blue litmus paper turns red to indicate acidic compounds. So blue litmus paper is sensitive to what? Red litmus paper is sensitive to OH ions. What do acids have? What makes an acid an acid? Right, and a lot of people remember from last term. It's sensitive to H plus ions. Acids are notorious for having H plus ions in them. For example, hydrochloric acid. The hydrogen is positive and the chlorine is negative, right? So once you know, right? Well, this is I know this is basic Form 3 chemistry, but I still need to remind you because it comes to CSEC. So here's the thing. Ammonia turns damp red litmus paper blue. Now, you have to use the word damp. When you're using the red litmus paper, you have to make sure the red litmus paper is a little wet first. Otherwise, it will not turn blue. That indicates what? That ammonia may be what? Acidic or alkaline? Well, which one is that sentence hinting at? If the ammonia is turning the damp red litmus paper blue, that suggests it's what? Alkaline, correct. Now, it's not really truly alkaline. It has to do with the water, right? The damp litmus paper. This is the actual reaction. When the ammonia, the NH3 gas, comes in contact with the dampness of the red litmus paper, the H2O means that that's the water on the red litmus paper, the dampness. You get ammonia hydroxide, okay? And the ammonia hydroxide, because the hydroxide is alkaline, it will do what? Change the red litmus paper blue. So that means, I just want to clear this up. The ammonia itself, pure ammonia, does not have any OH in it. So pure ammonia is not alkaline. It will not change red litmus paper blue. You have to mix it with the water first to get NH4OH, and only then it becomes alkaline. Okay? So I hope that that makes some sense. Now, there are actually two tests for ammonia gas. To me, this is the easiest test. You just dip red litmus paper in some water briefly and put it by the ammonia. And if it turns blue, well, ammonia gas is present. Right? Take down everything on the screen, even the two little notes at the bottom. I'll give it 3 minutes for that. All right. All right. So here is the second test for ammonia. Right now, this is going to take me a little while to explain, right? So bear with me, and you need to listen, right? Don't start to write to say, hey, I write it now, so I won't have to write later. Pay attention. Now, when people see HCl, right? When people see HCl, don't even you, I'm sure right now, and you're thinking about hydrochloric acid, and most people are thinking that. How much of you are guilty of that? HCl doesn't always mean hydrochloric acid. First of all, for something to be acid, it has to be dissolved in something. It has to be dissolved, right? When you see HCl, most of the time it is have what next to it? An AQ next to it. What does AQ mean? Aqueous, which means what? It's a solution, meaning that the HCl is dissolved, and most of the times it is be dissolved in what? Water, right? However, and this is hydrochloric acid, the HCl with AQ. But if you see HCl with a G, is that hydrochloric acid? The answer is no. That's just hydrogen chloride gas. It's not even fair to say that's hydrogen chloride gas acid. You can't even use the word acid there, because acid indicates or suggests that it's dissolved in something, and most of the times it will be what? Water. So HClG is really hydrogen chloride gas, and it is not considered to be an acid. So I just wanted to clarify that. That's the first thing. Okay. Now, hydrogen chloride gas is denser than ammonia gas. So one is denser and one is not as dense. Which one do you think will move faster, HCl or ammonia? Which one do you think will move faster? The dense one that is heavy, because if something is dense, I mean it's heavy, right? Or the less dense one? Right. So common sense would say the ammonia gas will move faster and the HCl will move what? Slower, right? Now, you cannot see HCl gas because it's colorless, right? Look at it, look, I have it up here. HCl gas is colorless, but it does have a smell, but believe me, you don't want to inhale it. Yeah, that could just mess you up really, really bad. And ammonia gas is also colorless. Now, look at this equation. When you cannot see ammonia gas and you cannot see hydrogen chloride gas. But when the two of them mix or meet, you get what? Ammonia chloride. And it is what? A solid. It's a kind of whitish solid to be exact. So while you cannot see ammonia gas by itself and hydrogen chloride gas by itself, when the two meet and they combine, you get something that you can't see. And some of you all are telling me, well, you did this experiment in school, and I'm not surprised. It's one of the most popular experiments. What you do, you get a test tube and you close it on both ends, a tube, and close it on both ends. One cotton ball is soaked with concentrated hydrochloric acid. Now, I just spent a lot of time indicating that we need hydrogen chloride gas. But if you soak this in hydrochloric acid, won't you get a vapor? Won't it eventually evaporate? It evaporates to give you what? Hydrogen chloride gas. And then on the other end of the tube, you put a cotton ball and you soak it in concentrated ammonia solution. That will give you this. And what would happen? The two gases will head towards each other because of diffusion. And you all notice that where the two of them meet, you will see a kind of white cloud of ammonia chloride. That's the solid ammonia chloride. But you all notice the ammonia chloride formed closer to the HCl side. You know why? Anybody can tell me why? Why the white cloud did not form exactly in the middle, like midway between the two gases? What's the reason for that? It has to do with the densities, right? And which one travels faster. And we now said the ammonia will flow faster. So the ammonia covers more distance because it moves faster, and the HCl gas is slower, so it covers less distance. So the two of them meet over here, closer to the HCl side. This experiment not only kind of shows that ammonia gas is present, but it's also used to prove that ammonia gas is less dense than HCl. So teachers use it for two reasons: to prove the presence of NH4 or ammonia, and to also prove that NH4, also known as ammonia, is less dense than HCl. Now, unfortunately, I needed to take down everything here, and I needed to draw this diagram as well. You need to memorize that diagram for the exam. Okay? Oh, sorry, let me not erase the little notes I made there, right? How much time you think will be fair for this? 10 minutes, because you have to draw a diagram. I think 10 minutes should be fair, right? I know this is boring. Yes, I know I talk and then you take notes. And you all know I just get bored when I can't talk, right? So this affects me as well. Right. So just a quick reminder, even though I did this just now at the beginning of class, remember, oxidation is the loss of electrons. And because you're losing electrons, remember, electrons have a negative charge. When you lose electrons, your charge actually becomes larger because you're losing something negative. So in oxidation, just remember the charge will always get larger, right? If something doesn't have a charge above it, it's automatically zero. So you see in all of these examples, the charge is getting what? Larger. So all of them are examples of oxidation, right? You don't have to take this down, I'm just reminding you. And reduction is the gain of electrons, right? When things gain electrons, their charges get smaller. And of course, if you look at all of these examples, right, all the charges are getting what? Smaller. Once again, if you see nothing hovering, like if something does not have a charge, that means the charge is what? Zero. So oxidation, charge gets larger. Reduction, charge gets smaller, right? So let's go, right? That's from last term. So what about sulfur dioxide, right? So sulfur dioxide is SO2. Now, sulfur dioxide is also colorless, but it has a very choking smell. It's a toxic gas, right? It's not something you want to be around. So this here is the test for it. And I'll explain all that madness at the bottom of the screen that looks scary. What you want to do is take the sulfur dioxide and bubble the gas through acidified potassium magnate 7. Last term, I spent a lot of time explaining potassium magnate 7, right? We spent a lot of time on that. What will happen? Potassium magnate, right, is naturally purple in color. And what it will do, if sulfur dioxide is present, it will change it from purple to what? Colorless. So the potassium magnate will lose its purple color. And don't worry, in the exam, the examiner is not gonna, you're not required to memorize this long equation, but I still want you to take it down. What will happen in the exam? The examiner will write down he will write down the equation for you, the balanced equation, and he might ask you some questions on it. That is how it will come in the exam. And the main reason for this, right? The most popular question they will ask you, well, explain why the potassium magnate loses its color. Why does it change from purple to colorless? And you will see that the question is worth like about 4 to 5 marks in the exam. So what happens, right? Well, when you work out all the oxidation numbers, right? Well, this here is the potassium magnate here, right? This here is the potassium magnate, KMnO4. When you work out the oxidation number is positive 7. The manganese, the Mn, has a charge of positive 7. And it's because of that positive 7, it has what? A purple appearance. The positive 7 charge for this particular compound is what gives it its distinctive purple color. But after you mix it with the sulfur dioxide and some water, you just get MnSO4. But when you work out the new oxidation number, you just get positive 2. And the positive, because the charge of the Mn change from +7 to +2. The +2 gives it a colorless color. Well, no color. +7 has a purple color, but the +2 for that similar compound has a colorless. And the examiner will want that in the explanation, right? It's because you will have to show him that you calculate the change in the oxidation numbers. It goes from +7 to +2. So quick question. The manganese, right? Was it oxidized or was it reduced? The Mn, was it oxidized or was it reduced? It started off at +7 and then it went to +2. It's a reduction, right? So the manganese was reduced. Who caused it to be reduced? The manganese was reduced from +7 to +2, but he didn't reduce himself. Who caused him to be reduced? Who is responsible for his reduction? Right, Kemi, correct. The SO4, he is the culprit. When something gets oxidized or reduced, he is not responsible for doing the reduction or oxidation. Somebody else is causing it. So the SO4 it comes like this. The SO4 went up to this and said, hey, I'm going to reduce you. And it reduced it from +7 to +2, which means the SO2 is your reducing agent. The reducing agent makes somebody else be reduced. He forces somebody else to get reduced. Well, as I mentioned last time, right? I know it's a long time, but I hope it rings some bells there. All right? I needed to take down everything on the screen, even the big long equation and the simplified one. The simplified one is the ionic equation. The ionic equation, as you all remember from last term, only shows the elements that have a change in charge. If somebody did not have a change in charge, it's not shown in the ionic equation, right? So the ionic equation is like a summary of the important things to pay attention to in the full equation. 5 minutes and we move on. Test. But first, let's pick 3 graves again and let's earn some money. I think you'll earn some rest here, right? Use 3 celebrities. I don't know if you all know all these celebrities here, right? But use 3. Luckily. Right? And any hand or skeleton hands that your grave has, you get an extra $5 as usual. Let me know how much money you have now. Somebody got 21, right? I see some of you chose me and expected the most money, but that was obviously a decoy. All right, let's go to the dungeon and rescue some of those prisoners. Right, so tell me who you're going to rescue, pay your money, get them out of that dungeon. Right? Get them out of that. Somebody said they're keeping all the money. They have no intention of rescuing. Nobody gonna rescue poor Gobby upside down in those chains. Somebody rescued Blood. Somebody rescued Donnie. All right, let's move on. All right, so now we have how you say, there's a slide here that looks like it came from the depths of hell. All right. So don't worry, don't worry. It's almost the same concept, right? There's going to be a change in oxidation number. So once again, we know SO2 is colorless and has a choking smell. But instead of using potassium manganate 7, we could use a different substance called potassium dichromate 6. And potassium dichromate is normally orange in color, but the sulfur dioxide will change it green. And the reason for it, right? You see, um, the, the potassium dichromate 6 over here, that's this substance here. They call it potassium dichromate 6 because if you work out the oxidation number or the charge of the chromium, it has a charge, guess what, of positive 6. So the chromium, the Cr itself is positive 6. I really don't care about what? The potassium, and I don't care about the oxygen. The Cr by itself, when you're analyzing it, is positive 6. After it mixes with the sulfur dioxide, the chromium gets a charge. Unfortunately, it goes from positive 6 to what? Positive 3. And I have the simplified or the ionic equation here. You all notice the chromium starts off as positive 6, and after the reaction, it changes to positive 3. The positive 6 is what gave it its orange color. And after it got reduced, and yes, it got reduced, notice it went from positive 6 to positive 3. After it was reduced by Mr. Sulfur Dioxide, the positive 3 charge gave it a green color rather than an orange color. All right? So once again, this equation here, you're not going to have to do what? Memorize it for the exam. The examiner is just going to ask you to calculate the charges of the chromium before and after. Or he might ask you to write the ionic equation at least after. That is on the syllabus. I know that. The ionic equations are on the syllabus, and it takes a little bit of practice to memorize it. So, sorry guys, you know what you have to do. Take it down, right? Take us 6 minutes. That should be fair. All right. So hopefully we won't have too much more to do, right? Some of you all are complaining that you are reading the comments here. All right, so at least we have an easy one here. Chlorine gas. Now, chlorine is easy to spot. Chlorine is a kind of yellowish, greenish gas. You can't miss it, right? And it has a sharp odor. It's definitely going to burn your nose, but it's seriously poisonous. If you see chlorine gas, run, right? Don't stay around for it. And chlorine gas, what it will do, it will turn moist blue litmus paper red. That means this has something to do with acids, because an acid will what? Do what? Change blue litmus paper to red, but it has to be moist litmus paper, moist blue. Well, what happens? The chlorine gas will combine with the moisture on the blue litmus paper, and it gives you what? The famous HCl, hydrochloric gas. Hydrochloric acid aqueous, right? The real hydrochloric acid. And it also gives you something, when you mix these two together, you also get HClO. Now, most people don't know what HClO is. You know what HCl is. HClO is something called chloric acid, right? Right. So what will happen, right? Well, I know it's on the screen, but I'm still going to say it. what will happen? The HCl part will change what? The moist blue litmus paper red. And after it changes red, the HClO will bleach the red litmus paper and change it white. And the examiner likes to ask that. They will ask which part of this equation causes it to change from blue to red. Well, it has to be the acid. And why does it get bleached white afterwards? It has to do with the chemical HClOAQ, the chloric acid. And I know it's probably obvious, but chloric acid is not the same thing as hydrochloric acid. Take down everything on the screen. This one is pretty short, so that's good news. Right, so that's how it. Oh Lord, I gave it a oh Lord. I hope you all didn't see that. All right, choose three for me. Choose three. I hope you. I pressed forward by mistake. I hope you all didn't see the money over it. So choose three celebrities and let's see if we get lucky. I see some people are happy for the game because they don't have to write. All right, so let's see how much money you guys got. Right, and remember the skeleton hand gives you an extra $5. Sum up your money, or should I say sigma your money, and we will go and, have a look in the dungeons. Yo. Anybody getting rescued today? Anybody getting rescued? Somebody has $75. Clearly that person is not rescuing anybody. Somebody rescued Michelle. Oh, Gobby got rescued. Gobby got rescued. Johnny got rescued. Rick got rescued. All right, so. All right, I think this is the last one here, guys, right? Nitrogen dioxide. Last one. Nothing too big here. Nitrogen dioxide, right? It's supposed to be properties, right, of the nitrogen dioxide. I put chlorine by mistake. It's a brown gas, and it has a sharp, toxic, irritating odor. What nitrogen dioxide will do, it will turn moist blue litmus paper red, just like chlorine, but it will not bleach it. So that's the main difference. The nitrogen dioxide will change, meaning that it's acidic in nature, but it does not bleach the paper afterwards. And this here is the reaction that you need to memorize for the exam, right? Now, take down everything. This is the last slide for the day, right? And one thing you need to know, we're far from finishing qualitative analysis. We only did gases today. We have 2 more sections to do. How to identify cations, that's things with a positive charge, and how to identify the opposite anions, right? Which have a negative charge. Right, so once you're finished, take down everything on the screen, and I know you all are tired. Feel free to leave, and somebody wanted me to go back to the first slide, so when I'm finished here, I will go back to the first slide.